Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Base-catalyzed H exchange at the alpha carbon requires 1. Removal of an alpha hydrogen by base to form an enolate, and 2. Reprotonation, here deuteration, by D2O. For this exchange to occur, the enolate must be accessible and stable. A key steric requirement is that the alpha hydrogen must be removable and the resulting enolate must be able to form. This requires reasonable orbital overlap between the alpha CH bond and the carbonyl pi system, and the carbanion enolate must not be excessively hindered. Step 1. Analyze option A. Cyclohexane 1,3 dione. This 1,3-diketone has alpha hydrogens at C2 between the two carbonyls. These hydrogens are highly acidic, pK-5,6, due to stabilization of the enolate by two flanking carbonyl groups. Base-catalyzed exchange proceeds readily. So, A does undergo exchange. Step 2. Analyze option B. 2-norbornene carboxyldehyde, bridgehead aldehyde. The aldehyde ChO is at a bridgehead of the norbornene skeleton. The alpha carbon to the aldehyde is the bridgehead carbon itself. However, looking more carefully at the structure, the ChO is attached to the bridgehead. The alpha hydrogens are on the carbons adjacent to the carbonyl. In norbornene systems, the alpha hydrogens on the IChO endo positions can still be abstracted. This compound can undergo base-catalyzed exchange because the alpha hydrogens on C1 or C3 adjacent carbons are accessible and the enolate can form. So, B does undergo exchange. It is not the answer by itself. Step 3. Analyze option C. Camphor 1,7,7-trimethylbicyclo 2.2.1 heptane 2-1. Camphor has a ketone at C2 of the norbornene skeleton, with gem-dimethyl groups at C1, the bridgehead C7,7 dimethyl. The alpha carbons are C1, bridgehead, quaternary, no H, and C3. At C3 there are alpha hydrogens, the ICOH at C3. However, the critical issue is that camphor is extremely resistant to base-catalyzed H exchange despite having alpha hydrogens at C3. The reason is steric. The gem-dimethyl groups, the two methyl groups at C7, create severe steric hindrance around the carbonyl phase, making it very difficult for base to approach and abstract the alpha hydrogen. Furthermore, even if the enolate forms, reprotonation deuteration is hindered. Camphor is a classic example in textbooks of a compound with alpha hydrogens that does not undergo base-catalyzed exchange in D2O due to steric inaccessibility. The IChO phase is blocked by the gem-dimethyl bridge, and overall the rigid bicyclic framework with bulky methyls prevents the reaction. This is a well-known fact used in total synthesis. Camphor-derived auxiliaries are stable under basic conditions. Step 4. Why not D, both B and C? Option B. 2-norbornene carboxyldehyde does undergo base-catalyzed exchange because the aldehyde alpha hydrogens are accessible, less sterically hindered than camphor. Only camphor uniquely fails to exchange despite having alpha hydrogens. Step 5. Conclusion. Only camphor, option C, fails to undergo base-catalyzed H exchange in D2O despite possessing alpha hydrogens, due to severe steric hindrance from the gem-dimethyl groups blocking base access to the alpha hydrogens. Therefore, the correct answer is C. Therefore, the correct answer is option C.